Thank you very much. Okay, so good morning. Switching gears a little bit today, I want to talk about particle transport, so energetic particles. So my name is Giacalone. I'm a professor at the University of Arizona in Tucson. My research specialty is understanding high-energy charged particles in the heliosphere predominantly, but I also do a little bit of astrophysics, but primarily heliospheric phenomenon. And I focus mostly on solar energetic particles. You know, how does the sun accelerate particles to extremely high energies, and what's the physical processes behind that? But I'm not going to talk too much about that, actually, in these two lectures I'm going to give. The two lectures I'm going to give today, the first one is really just mostly an overview of galactic cosmic rays primarily, although much of the physics translates over to solar energetic particles. It also translates to the galaxy and so on and so forth. But I'm primarily just want to kind of give an overview of the process in the first 45 minutes. We'll see how long. I mean, my lectures, I tend to prepare in a way that I don't time them exactly right. They're kind of like a newspaper article that I kind of do most of the stuff that I need to at the beginning, and then if it filters out, I mean, if I stop at some point, I can just stop. Okay, so we'll see how far I get. But anyways, please interrupt if you don't understand something. If I've misspelled something, please say that's a misspelling or anything. Just please interrupt. I'm more than happy to answer questions. Oh, I need to share this, I guess. Oh, I'm good? Okay. Oh, there we go. Okay, well, there we go. So I got two lectures. The first lecture is just total background. I think I have one equation. We discussed it very briefly yesterday about the scale size of the heliosphere and that you're balancing the pressure of the interstellar medium with the outflowing ram pressure of the solar wind. So I have one equation that basically says that in the first lecture, but that's the only equation. It's all general background. The second lecture, I do want to get into a little bit of the physics of charged particle transport and what cosmic ray physicists and solar energetic particle theorists and numerical modelers tend to, the basic underlying physical principles behind that. So I want to go into that. And primarily, I want to go through the derivation of something called the Parker transport equation. I'm not going to do it the way Gene Parker did it in 1965, which is a pretty tedious set of steps. I don't want to do all of the algebra. I just want to kind of do it from a sort of heuristic, intuitive viewpoint, and then just sort of lay down the equation, and you'll understand where all the terms come from. And that's basically what cosmic ray physicists do, okay, is solve that. So that's the second lecture. The homework set is kind of where I do the application. I'll give kind of a warning. I do have the homework set, and a couple of them you can do based on things I've talked about today, but primarily a couple of the problems kind of come from the textbook. And I don't know if you all have the textbook with you or not. I hope you do. If you don't, we can go over them. That's what the school's about. Okay, I think that this sort of slide has been discussed before. The heliosphere so first of all, the sun is obviously inside the galaxy, and the sun has this expanding solar wind, and the solar wind blows a little bubble called the heliosphere, and it's very similar to what we see around other stars. So we know this happens throughout the universe. It's not just our own solar system. We have these sort of little bubbles like this, and this is actually emission that we measure, Lyman alpha and these kinds of things that tell us that we've got these astrospheres, which are basically analogous to the heliosphere in our own solar system. Now, the ideas for this were first postulated by Gene Parker, and by the way, I'll say this, if you are in this field for very long, you'll realize that Gene Parker has probably done a very large amount of what you're going to encounter in this field. He's written many, many papers in solar physics, heliospheric physics, energetic charged particles. I love to say it this way. He was at the University of Chicago when he was writing down the equations for the solar wind for the first time, describing the solar wind. He was doing it at a time when nobody believed it. Okay, so he was really at the leading edge. Nobody believed what he was doing. Okay, so he was doing these equations basically unopposed. I mean, so he was basically solving the MHD equations for various phenomenon because nobody believed it. So he was writing paper after paper after paper, and so you find that his name is in many of these original papers. And you'll find, as I'm finding quite humbly now, I have a new idea and I say, oh, I'm going to go do this. And I go back in the literature and I find that that's something Gene Parker did back in 1956 or something. So he also was the first to describe the size of the heliosphere. Okay, and so he had the MHD equations, which I think you've all seen. And he just described the streamlines of the flow. This would be the flow of the interstellar gas up here. Unfortunately, the laser printer, I could barely see it yesterday. I don't know if you can see it. The interstellar, these are like streamlines of the interstellar flow. And this is the solar wind flow coming out. And you have this boundary where if you balance so this entire scale size is set by the boundary conditions of the sun. So the origin of the solar wind, what is the speed of the solar wind, and the density, and so on and so forth. Okay, and you can work out, if you balance that ram pressure, the ram pressure of the solar wind, which is the dominant pressure. It does carry a magnetic field, but that magnetic field's quite weak. The solar wind has temperature. It's pretty hot. I mean, the solar wind is actually fairly hot, but it's still small compared to the ram energy. So it's another way to think about it. It's a highly supersonic flow. And it's a highly super-alphanic flow. So the magnetic field is weak and the thermal pressure is weak. But the ram pressure is the dominant one. But it gets weaker and weaker because the density falls off as 1 over r squared. And that, at some point, it encounters the interstellar medium. And the interstellar medium then is the dominant pressure. And, of course, when those pressures sort of balance, you get a scale size. And just by noting that rho falls off as 1 over r squared, taking your best guess at the pressure of the interstellar medium, which at the time he didn't have a very good guess. He had it to within a factor of anywhere between 1 and 4 times 10 to the minus 12 in CGS units. And with that guess, the best guess he knew roughly the solar wind speed and the density at say 1 AU. And then he was able to estimate the scale size of the heliosphere. And strangely enough, it's not far from what we measure today. The Voyagers have crossed this boundary, and it's not far off. Parker was actually quite close, given what he knew at the time. By the way, this is probably it's a movie and it doesn't show up as a movie, but this is probably the best simulation of the heliosphere you're going to find. I think you all roughly recognize what's being shown here, right? So this is a water spigot. This was actually a planetarium exhibit in a science museum at the University of Arizona at Flandreau Planetarium, and it's basically, you can see the sun. The sun is orange, okay. And this is a water spigot. The water comes out, and the water flows out. It actually flows out faster than the characteristic wave speeds that you get in this kind of a situation where it's flowing out over the surface. And so it's actually very analogous to the solar wind. It's supersonic in that sense. It's faster than the characteristic wave speed. And over here, actually quite clever, the designers of this had another sort of water spigot out here with a bunch of little holes in it that represented the interstellar medium. And there was little soap bubbles added to it. So you could see the separation of the interstellar medium with the solar wind. And quite interestingly, you get this inner boundary, which is the termination shock. So the solar wind is supersonic, and the interstellar medium, so when it goes from supersonic to subsonic, but still solar wind, this is still solar wind, that happens through a shock transition. So that's the termination shock, and both of our Voyager spacecraft have crossed this now. And then there's perhaps another shock, although there was a paper out a couple of years ago by the IBEX team, NASA spacecraft called IBEX, which, I don't want to go into the details of that. But they have made a determination of the interstellar flow speed and have basically determined that it is probably subsonic. So there's probably not a shock wave out here, but if there's one, it's very weak. But in any event, this is roughly what the heliosphere looks like. Okay? You could run a numerical simulation. You could run the magnetohydrodynamic. You can solve the magnetohydrodynamic equations. I should say the heliosphere system is actually quite complicated. You might be interested to note that the neutrals, the interstellar neutral gas, far dominates in terms of number density at the distances that we're talking about way out here. Okay, so the MHD equations, and charge exchange is a very important process, so that typically has to be included in as well. It's a complicated problem, but it can be done. Okay, but there's obviously groups that do it, and it's a problem that can be solved. But it's not just simply take the MHD equations and solve them. You usually have to add source terms and things like that. Okay, well, this is a cartoon illustration of the heliosphere. The termination shock, as I mentioned, you can see the orbits of the planets in here. So the termination shock is quite some distance from the sun. It's about 90. Let's see, Voyager 1 crossed it, I think it was 94 AU. Voyager 2 crossed it, it was some 10 AU less. And actually that difference, Voyager 1 saw that it was farther away than Voyager 2. And Voyager 2 are basically taking, interestingly enough, Voyager 2 was launched before Voyager 1, but because of the way they encountered, basically they were planetary missions, but because of the way they encountered the planets, they end up having Voyager 2 is a little bit lagging behind in terms of radial distance. And they're going in opposite directions relative to the ecliptic plane. One's going up and one's going down. Okay, that difference in distance has actually been attributed to the interstellar magnetic field being squashing in the heliosphere on one side. And so when it does that, it produces a slight asymmetry. That's one interpretation. And I think that's probably the most common interpretation right now for that distance difference. This region here is called the heliosheath. Both Voyagers are in the heliosheath right now. Both of them have crossed this boundary. And I should say that there's two types of heliosheath. There's what's referred to as the inner heliosheath. The inner heliosheath is solar wind plasma, okay, that's just been shocked by the termination shock. It's slower. It deflects around, so the flow tends to go back off to the sides this way. But it's still solar wind. If you were measuring particles and you asked where those particles came from, they came from the sun. Okay? But once you cross this boundary, you go out into what's called the outer heliosheath. The outer heliosheath is interstellar gas. And there's a big issue right now as to whether Voyager is actually across this boundary. I put a little yellow dot. It may be here. Okay, we're not sure whether we're there or not. If I have a little bit of time at the end of my, at the end of this 45 minutes, I want to discuss the latest observations by Voyager. Okay. All right. I always like to have a slide like this. I always have to explain to people why I do what I do. Why should anybody care about the heliosphere? Why should anybody care? Why should scientists care? Why should the general public care? Okay. I've listed it, and I always scratch my head to try to find some really good reasons, okay? And maybe you guys can have your own set of reasons, okay? But a couple of reasons. First of all, the heliosphere actually represents the boundaries of the heliosphere, the termination shock, the heliopause, that's that separation between solar wind and interstellar medium. They actually represent the first of a few boundaries that galactic cosmic rays that come from outside our solar system into the solar system, that they get modulated. They get slowed down by the solar wind and they get swept back out by the solar wind. So the heliosphere represents the first of several boundaries that shield us from galactic cosmic rays. Thankfully, the last boundary is our atmosphere. If it weren't for our atmosphere, we would be continually bombarded with cosmic rays, and that would not be good. I doubt life would have formed in such a situation. Cosmic rays move extremely fast. They're moving the speed of light. They have a lot of energy. The highest energy cosmic rays we observe, like 10 to the 21st electron volts, the kinetic energy of a single proton is roughly equivalent to the kinetic energy a bowling ball would have if I dropped it from this distance on my foot. Okay, one proton. Okay, so thankfully only one of those hits every couple of years, the Earth. Okay, so it's not, and those actually do have enough energy to penetrate through the atmosphere, but or at least a good way through. But anyways, the atmosphere is the last of the boundaries. The magnetosphere, of course, is another boundary, and so on. But the cosmic rays have a long way to go from 100 AU to 1 AU. I would also add that NASA has invested an awful lot of money in studying the sun. Okay, they've got a lot of missions up there. NASA is very good at launching missions, and there's many missions. Voyager's out there. IBEX is IBEX is actually a Earth-orbiting spacecraft. If you don't know about IBEX, it's an orbit about Earth, but it measures neutral particles that come from outside the solar system that are produced by processes having to do with things outside this, or well, in the distant reaches of the heliosphere. ACE is something that sits at L1, the Lagrange point L1, between the Earth and the Sun, and it measures primarily the composition of cosmic rays and solar energetic particles and plasma and fields and so on. Ulysses was mentioned yesterday, I heard, and it's no longer working, but that was also aimed at studying. All of these are aimed at primarily understanding the heliosphere. Very rich data sets. Lots of PhD projects are still found in the data sets from these missions. and many, like any other NASA mission. It's also important laboratory for studying multi-component plasmas. As I mentioned, the heliosphere has the neutral particles play a very important role far away, not at 1 AU, but at 100 AU, neutral particles play an important role. Charge exchange, what are called pickup ions. These are neutral particles that have become ionized and then get subject to the E&M forces from the solar wind. These are called pickup ions. Pickup ions, actually, they're what are called superthermal particles. They're not part of the solar wind Maxwellian-like distribution, so that's another species of particles. You've got cosmic rays. As in one of the homework set problems, actually, you work out the number density of cosmic rays at 1 AU. And I also ask you to work out the energy density of cosmic rays at 1 AU. Now, at 1 AU, both of those numbers, well, the number density is always pretty small compared to everything. The energy density of cosmic rays is small compared to the relevant energy density of, say, the solar wind at 1 AU. But that's not true at 100 AU. At 100 AU, the cosmic ray energy density is about an EV per cubic centimeter, and that's roughly the same as, say, the magnetic field pressure and things like that. So cosmic rays can play an important role. And for me, as a theorist in studying energetic particles, there are many physics problems. I mean, space physics, to me, has always been interesting. The basic fundamental equations that govern what we do were really written down by Newton and Maxwell, okay, many years ago, right? But there is so much elegant physics that can be done with all of that, okay, because of the subtleties and trying to understand, especially, well, primarily we're constrained by an enormous number of observations. And so trying to understand and deconvolve what you're seeing with relatively straightforward equations that we think we understand has turned out to be a major challenge. Okay? At least I found it to be quite a challenge, quite rewarding. I'm actually very happy that I do what I do. So there's a lot of interesting physics questions. There's no shortage of PhD projects in this field. Okay, let's see. I'm already, as my usual thing, sometimes I start babbling, and next thing I know, I'm 3 slides in, and it's taken me 45 minutes. And I haven't even had any questions yet. So, but I will show this slide, and I just want to mention a few things. The heliosphere has many energetic particle populations, and I just want to go through them as quickly as I can. Okay. This slide actually is one of these nice slides that were produced for the ACE mission. When ACE was launched, roughly, they wanted to demonstrate the ability of the instruments on the ACE mission. So what it's showing is energy spectrum, which I'll talk about in the second lecture, versus kinetic energy. And it's showing a whole bunch of different populations of particles. And down here are the energy coverage by the instruments for this mission and the names. So SWICS and SWIMS are measuring solar wind plasma and pickup ions and that sort of thing. ULICE and SEPICA are measuring charged particles. SEPICA measures charged states predominantly. Oh, and then CIS and CRIS measure cosmic rays at high energies. Okay, and so you see it covers the full energy range, it covers the full spectrum. Okay, so in the solar wind, there's fast and slow solar wind. That was, Carl discussed that. Fast and slow solar wind. Their distributions are Maxwellian-like at low energies, but no distribution that I have ever seen in space, observation, is a pure Maxwellian. I've never seen a pure Maxwellian, an observation of a pure Maxwellian. So the Maxwellian comes about when you have lots of collisions. If you have lots of collisions, that process gives rise to a Maxwellian distribution. There's always a high energy tail in space, though, because the so kappa distribution is also, that would be the tail. So anything with a tail would be a non-Maxwellian. That's what I'm referring to, yeah. So if you have a tail, then it's non-Maxwellian, right? It's Maxwellian-like at low energies, okay? But it's not you always have a tail. Basically, that's the message, is that you always have a tail. Okay, and so yeah, so down here you get this little tail. And the quiet time tail is actually an issue of study right now. People are trying to understand what is the quiet time tail. But that's hard to do because you have to decide what's a quiet time. Okay, you have to decide what's quiet. Is it quiet now? Okay, it's kind of hard to figure that out. So actually measuring the quiet time is actually a challenge in and of itself. But anyways, 2 different solar wind peaks because there's 2 different speeds of the solar wind, as has been discussed. Okay, I'm not going to discuss these co-rotating events, but because the sun rotates there and because the magnetic axis is offset from the rotation axis of the sun, and the high-speed, low-speed difference of the solar wind is actually is governed by the magnetic axis, not the rotation axis, that you have during solar minimum conditions, you have periods of time when high-speed wind is always overtaking slow-speed wind, and it just co-rotates with the sun. These events actually are known to produce energetic particles, and they tend to be lower in number, but you can see them. That's an area of study. Solar energetic particles tend to be fairly high energy phenomenon from the sun, much lower than galactic cosmic rays. Galactic cosmic rays that we see at Earth are the highest energy particles that we see. But some solar energetic particle events can get up to pretty high energies. Then there's ESP events. Okay, I'm going to inundate you with all these terms. ESP, I believe, stands for energetic storm particle. Other people have different definitions, but that's my definition. Energetic storm particle events. SEP is solar energetic particle. Okay. The difference is, let me just tell you the difference. I have a slide. The difference is this. It's really not a big deal. First of all, the sun has a flare. It also has coronal mass ejections. And then you often see this snow on the detector. This is a LASCO image. And this snow on the detector is noise. It's actual particles hitting the CCD camera. These are SEPs. If I count them up at 1 AU, intensity versus time, you see the rise happen early. So you see the particles coming from the event very quickly because they're moving fast. These particles are not quite the speed of light, but electrons are the speed of light, but the ions are moving at some fraction of the speed of light. The entire event is called a solar energetic particle event. But the ESPs are the ones that are the most intense that are associated when this coronal mass ejection finally crosses you at 1 AU. So, or not the mass ejection, but the shock that it's driving. When that shock goes past you, you see another little bump of particles. That's where the most intense event is. Those are called ESPs. And they don't always go up to high energy. So the shock is not necessarily accelerating particles to really high energies locally when it crosses you. So you often don't see a bump at the highest energies. So that's why if I go back to this slide, the ESPs fall off. They don't go up to as high energies as the entire event. Okay? Then there's anomalous cosmic rays. Anomalous cosmic rays these are particles that we think, and I think that they're accelerated at the solar wind termination shock. So interstellar neutral gas comes in, becomes ionized, gets carried out by the solar wind. These are called pickup ions. These pickup ions are super thermal. They encounter the termination shock of the solar wind where they get accelerated to fairly high energies, much higher than SEP events, but much lower in intensity. And these are referred to as anomalous cosmic rays. And there's some debate. Sorry, yes? Right, yeah, good question. Yes, because I love this topic, yeah. So, okay, so, yeah, this is a good point, and I wish I had some slides on this. Okay, so my interpretation of this is this. So let me just summarize what you're saying, is that if you look at the anomalous cosmic ray energies, the higher energies predominantly, like the ones at 100 MeV or 10 MeV, and if you look at the intensity at the crossing of the termination shock, you'll see that those particles didn't peak at the shock. You would have expected them to peak at the shock if the shock was accelerating them. Okay? The lower energy stuff, the much lower energy stuff, in fact, actually did peak at the shock. I mean, the shock, 2 orders of magnitude, you had a big jump of particles from 50 keV to an MeV. Those energy ranges were definitely accelerated by the shock, but the higher energy ones didn't peak there. Okay, so there's been a couple of there's been a big debate in the community about why that is. Okay, some ideas have it that you have another acceleration mechanism that accelerates these particles throughout the heliosheath. There could be some sort of statistical acceleration process which, through random plasma compressions, which maybe I can get to the basic physics of in the second lecture, that accelerates these particles. But that has to be done very, very far out. Okay, and so what's happening is that as you're getting to the outer boundary, you're starting to see these high energy particles. Another idea is that it's magnetic reconnection. Magnetic reconnection, the heliosheath actually, you could have magnetic reconnection through either turbulence or the heliosphere current sheet gets compressed together and you can have magnetic reconnection. That could also accelerate the particles. Both of these ideas are, I think, are on the magnetic reconnection idea. I think has an issue with the magnetic field strength is just a little too weak to produce all of these anomalous cosmic rays that we see. The compression acceleration idea, I think that at least the quantitative stuff that's been described to explain the ACRs hasn't stood up to scrutiny, I think. So the other interpretation is that the particles are accelerated elsewhere on the shock at high energies, and they simply diffuse over to that region. That's the idea that I've sort of championed and like. I've just only been in, I love talking about it, although I have not done any quantitative calculations myself. But anyways, that's a very good point. The final thing I want to mention is galactic cosmic rays, which have this little rollover like this. And that's, now I'm going to start talking about that. 9 o'clock. Okay, so I'm supposed to finish up in 15 minutes. Okay, anomalous cosmic rays I mentioned. Okay, galactic cosmic rays come into our solar system, are modulated by the solar wind. So the solar wind is flowing outward. Cosmic rays are trying to swim upwards in that, okay, and they end up being reduced in number. Now, the highest energy cosmic rays don't care about the solar wind. So cosmic rays at 10 to the 12th electron volts and above, they just move straight lines through the heliosphere. They really don't care about the solar wind. Thankfully, there's not a large number of them. There's actually some very interesting physics that you can do, though. Strangely enough, you can measure things like the magnetic field strength of the sun by looking at the deflection of these cosmic rays as they go. See, if you look towards the sun at cosmic rays at high energies through air showers and these other things, you'll see that the disk of the sun, which is opaque to cosmic rays don't go through the sun, of course, you'll see that the disk of the sun as seen in cosmic rays is offset from the actual where the sun is. And that offset is due to the magnetic field of the sun. So there's actually some very interesting physics that can be done with that. Nevertheless, they come in, they get reduced, and let's talk about how that happens. So there's the well-known anti-correlation between the sunspot number and the cosmic ray intensity. Okay, I don't know whether you all know that or not, but I'm just stating this as a fact. So if you plot on one axis the number of sunspots on the sun, which has an 11-year cycle, and then you plot below that, in this case, this is the count of neutrons through a neutron monitor, but it's directly related to cosmic rays striking the upper atmosphere of the Earth. You see that the cosmic rays are high when the sunspots are low. Here it's high. Here the cosmic rays are high, the sunspots are low here. And this is actually a very important anti-correlation. Any study of the sun that goes back in time, thousands of years through carbon date or through analysis of tree rings or through ice cores, beryllium-10 and these sorts of things, which then says the sun was less active or more active during periods of time, is drawing on this correlation. Okay? That's because the beryllium-10, carbon-14 are produced by cosmic rays. They're produced by nuclear processes in our atmosphere and produced by cosmic rays. So what you're really measuring is the intensity of cosmic rays, an indirect measure of the cosmic rays. And then through this relationship, we can say what's going on with the sun. So it's a very important anti-correlation. You might also notice, by the way, and I will talk about this peak is kind of triangular shaped. This one's flat. This one's triangular shaped. This one's flat-ish. Okay? This one turned out to be triangular. The next one is flat. Okay? This is actually the 22-year cosmic ray cycle, which I'll discuss. It has to do with the Heliosphere current sheet and drifts. Yes? Mm-hmm.
Do you have any evidence of this correlation for the cosmic rays, or would you expect it also a long-term modulation?
Well, cosmic rays have really only been, well, they were discovered in 1912, okay, by Victor Hess. So cosmic ray studies didn't really start kicking off until roughly the 50s. I'm not aware of actually cosmic ray records. Actually, this is probably about as early as the UGO, like 1960 on here. So the correlation between, so yes, they've been counting sunspots for much longer than they have cosmic rays, is basically the message I would give. because cosmic rays haven't been studied quite as far. I mean, they were found in 1912, and it probably didn't start understanding this correlation until a little bit later. I don't know, does that answer the question, basically? Because we didn't have cosmic ray measurements back in, let's see, the sunspot number cycle actually goes back to the late 1700s, I think. They were measuring sunspots before that, but because of the Maunder minimum, when sunspots went away, they didn't actually see the solar cycle till a little bit later. I believe that's the correct interpretation of the sunspot. So we're aware of the 11-year cycle, but we weren't aware of cosmic rays until later. I don't know, does that answer?
Well, I mean, what I wonder is, like, if there was some evidence, of course, we don't have, data as far as the sunspot, but would you expect
Okay.
reconstruct the past?
Yeah. So maybe what you might be asking is, can you see the 11-year cycle in something like tree ring data or beryllium-10? That might answer, because you would expect that if this correlation were to exist forever, basically, and there's good physical reasons to expect this, and that's kind of what I'm going to talk about. There's good reasons to expect this correlation. But would you see an 11-year cycle in tree rings and things like that? Actually, that's a little bit controversial, but I believe that the answer is yes, that you can see an 11-year cycle in tree rings. But I think that actually is a little bit of an art form, okay, extracting out the cosmic ray signal from tree rings and ice core samples and things like that. But yes, you would expect it for good physical reasons, actually. And the basic, I'll just keep talking, but for good physical reasons, you would expect this correlation to exist. And this is the tree ring that I just talked about. So this reconstruction this is actually a measure of the sun's activity going back almost 100,000 years, 10,000 years, excuse me. Okay, and this is done with that correlation. Let me just say one more thing about galactic cosmic rays. They pose a major radiation hazard to humans in space. This slide was provided to me by Dick Maywalt, a colleague of mine, where he pieced together studies of the radiation dose equivalent that a human body experiences for cosmic rays of a certain energy behind certain kinds of shielding. That's a separate calculation that there are actually experts here in this building that do similar sorts of things. This is the 6-month dose equivalent in particular units having to do with radiation dosage as a function of time. This is actually the cosmic ray cycle. This is the peaked, flat top, peaked, so the flat, peak, flat, peak. Okay, but it's been converted to radiation dose equivalent. And this is just galactic cosmic rays behind standard shielding. Okay. By the way, galactic cosmic rays are very difficult to shield. They're just very energetic, very difficult to shield. Solar energetic particles you may be able to shield. They're lower energy, a little bit less penetrating power. But GCRs, hard to shield. So it's not cost effective to go up and throw 3 meters of metal, okay, between you and the cosmic rays. So anyways, this is the dose equivalent for a 6-month mission between Earth and Mars. So taking the galactic cosmic rays measured at Earth primarily, Mars isn't that much farther out. Okay, and that dashed line is the NASA limit. Yeah. Yes. Yeah. Protons dominate the largest events in both cases, but yes, there are differences in the composition. Yeah. Electrons are about a factor of 100 times less in galactic cosmic rays. Solar energetic particles often have a very, they're rich in, well, it depends on the event. I mean, there's a whole slew of events from solar energetic particles, but they can be rich in all sorts of different things like helium-3 and heavy ions and things like that, which you don't often see in galactic cosmic rays. So yes, there is a sort of a fundamental difference between them, yeah. But in both cases, the biggest events are dominated by protons. But anyways, the point here is that it takes longer than 6 months to get to Mars, okay? Maybe even, I don't know, look, you got to get there and then you got to get back. And then you got to be on the surface of Mars, which is a very thin atmosphere, probably doesn't provide you a lot of shielding, because actually when a cosmic ray strikes the atmosphere, it produces a shower of particles. So you've taken that one cosmic ray and now it hits the atmosphere and produces several more. Those several more particles are all moving pretty fast with lots of energy. It takes a while to dissipate. And there actually is a layer, what is referred to as the Pfotzer maximum, that's the peak. You don't want to be at the Pfotzer maximum is what I'm trying to say, is because you're producing too many particles, all with lots of energy. At some point they dissipate, so you're okay. Lower atmosphere, you're fine. But if you're at some point in the atmosphere, you're actually being bombarded by more than just that one cosmic ray, by lots of others. Okay, so there is a place, and the surface of Mars might be roughly at the Pfotzer maximum. I'm not so sure that calculation's been carefully done. But the bottom line is Mars' surface probably doesn't afford you a lot of protection. Okay, okay. Anyways, it's almost a non-starter. Yes?
That kind of suggests that trips to Mars must be made at certain times.
Ah, yeah. I think that's a very, I think they've got to be considering things like this, yes. So if you go during solar minimum, then you have the problem that I'm mentioning right now. So in other words, the peaks are during solar minimum. But you could go during solar maximum, and of course we got no problem with GCRs. But then we got to worry about the solar energetic particles. And solar energetic particles are, so this is, let's just look at this plot right here. So underlying is the galactic cosmic rays. This is a shorter period of time. It's lower energies measured by ACE. But besides the sort of background GCRs, you have these random events that sometimes are 1,000,000 times more intense. These are lower energy. These are not the highest energy galactic cosmic rays. They're not GeV. These are down around tens of MeV. Probably can shield from those. So maybe going during solar maximum is the time to go, but you wouldn't want to be up there during like a Carrington-like event, okay? And we had a Carrington-like event last summer that was seen by Stereo B. Okay, if that had been directed at Earth, that would have been an interesting, geomagnetic storms and so on and so forth that resulted from that. Okay, so this is that's what this is. This is the galactic cosmic ray spectrum measured at all energies over a whole bunch of different experiments. It's just sort of all put together into one big picture like this, and this modulation that you see at low energies is the modulation caused by the solar wind. Okay, so it turns so low energy galactic cosmic rays don't make it in. These low energies don't make it in. The higher energies come in more or less unimpeded, but the lower energies get modulated by the solar wind. Okay, cosmic rays vary on many scales. I think I'll skip that slide since I'm down to just a few minutes. I want to say a couple things. The cosmic ray motion inside the solar system is really a combination of 4 main physical effects. One is spatial diffusion. Okay? Yes, cosmic rays are individual charged particles, and they're not hitting other charged particles. Okay? So they're not actually doing particle-particle collisions. Yet the process can be described as being diffusive. The reason is that the magnetic field of the solar wind fluctuates. It's not just a perfect, constant magnetic field. Okay? You've got turbulence in the magnetic field. Those wiggles in the magnetic field, if anybody, it's a nice exercise to do on a computer. Solve the charged particle Lorentz force equation with a wiggly magnetic field. Make the wiggly magnetic field have a wiggle of the scale roughly the same size as the gyro radius of the particle. If you do that, now look at the particle, look at the orbit. You'll see that it's sort of bouncing all over the place. Okay? That's a resonance. That is basically a form of diffusion. So, and in fact, the diffusion coefficient in a diffusion equation depends on the wiggling of the magnetic field, the turbulence in the magnetic field. So, spatial diffusion. And the diffusion is complicated. You have diffusion along the magnetic field and across the magnetic field, tend to be different. Okay? There's also convection with the flow. Okay, that's basically when a particle scatters in the sense that I just talked about, it actually scatters. It does so in a way that it's conserving its energy in the local plasma frame. But in a frame moving with the solar wind, it is when the energy is conserved in that scatter. So that translation you have to include in the transport of the particles. And so convection with the solar wind is a big effect. Think of it this way: they're swimming against the solar wind. The solar wind's trying to sweep them back out. Okay. There's also drifts. If you've taken any class in sort of plasma physics, basic plasma physics, and you start getting into charged particle motion, you'll find that there's large-scale drifts, something called the gradient drift. When you have a gradient in the magnetic field, you'll get a drift of the particles. Magnetic field line that's curved will lead to a curvature drift. Both of these are large-scale effects, things that are much larger than the gyroradius of the particles. And then it's very important to include energy change. Energy change, actually, any proton in the solar wind, if you take a proton or electron, you put it into the solar wind and you just drop it into the solar wind, it will lose energy, okay? Barring compressions or shocks or any of that sort of stuff. But the quiet time solar wind, it loses energy. That's because of adiabatic cooling. So cosmic ray modulation has actually been thought of as being the result of adiabatic cooling. So energy change has to be included. And the acceleration of particles by shocks is also included in this as well. Energy change comes from expansions and so on and so forth in the plasma. Yeah, let me just say a couple things so let me go to a slide that I think might be interesting or more relevant here. Okay, so I want to finish with just a couple of thoughts here, and then we'll take a break. Okay, so all of these effects have been included in a model. You solve something called the transport equation, which I'll talk about in the second lecture. And when you do that, you come up with this sort of general cartoon illustration for what cosmic rays do when they come inside the solar system. So cosmic rays come in. They're not moving in straight lines because, well, the lower energy cosmic rays are not moving in straight lines. They're doing a random walk. It's a scattering process, so they're undergoing a random walk. At the same time, you've got the solar wind, which is trying to keep them out. And you also have the current sheet. So the magnetic field is in one direction in one hemisphere. It's in a different direction in the other hemisphere. So that also leads to a drift. And so all of these effects have to be included and leads to a modulation of the cosmic rays. This would be during solar minimum, the heliospheric current sheet, which separates the northern polarity and the southern polarity of the magnetic field, tends to be fairly flat. The ballerina skirt tends to be fairly flat during solar minimum. It's much more wavy during solar maximum. But during solar minimum, it's quite flat. Cosmic rays more or less have easy access. They're still battling diffusion and are still battling advection with the flow and energy change, but they have more easy entrance into the solar system. During solar maximum, you have lots of these transient events, coronal mass ejections that merge. You have global merged interaction regions and other barriers. The magnetic field has these large transient events that cosmic rays just get swept out of. Okay? And actually, you can observe that on a local level, something called a Forbush decrease. Very large coronal mass ejection will go by, and if you look at galactic cosmic rays, it goes way down right when the CME goes by, and then it takes about a couple of weeks to recover back. Okay? So you can see that effect locally as well, these barriers. But if you have lots of these things, like which you do during solar maximum, the cosmic rays just say, okay, I give up. I'm not coming in. I'm not going to make it to Earth this year. Okay? And so the cosmic rays are lower during solar maximum. And the last thing I wanted to show, this is the heliospheric current sheet, which hopefully you've seen because I'm going past it at warp speed here. And I just described it anyways. Okay, so I just wanted to point out the 22-year cycle, what causes the 22-year cycle. And then I'll stop here, and then I think I'm going to take a couple of minutes at the beginning of the next lecture to talk about something topical. In any event, the cosmic ray patterns, when you solve all of these equations, actually tend to be governed by the orientation of the magnetic field. So I'm sorry for the green. The green just is horrible. But anyways, this is the heliospheric current sheet. The circle is this heliosphere. It's not a sphere, of course, but it is to a theorist. And this is the heliospheric current sheet. And these red arrows represent the streaming motions of cosmic rays depending on the polarity of the magnetic field. So during this configuration, and you might ask me what A refers to, and I went and dug through the literature last night and realized what A actually is. A is actually the signed value of the magnetic field times the radius of the sun squared at the surface of the sun. I always thought it had something to do with like the vector potential, some complicated thing. But no, it started in some paper that Randy Giacalone wrote with Thomas, and he had expressed the magnetic field as A over R squared times R hat something or another. So the A is actually B0 times the radius of the sun squared. Okay. But nevertheless, this just means that the magnetic field is outward in the northern hemisphere and inward in the southern hemisphere. Okay? In this configuration, cosmic rays, if you work out the drift patterns, tend to be coming in over the poles of the heliosphere, and they go back out. These are patterns that are continuous patterns, and so they go out along the current sheet, They drift along the termination shock, and these are the drift motions. So these are the drift motions that you would expect. Okay? So in this configuration, cosmic rays coming in from the northern hemisphere, they have very few, during solar minimum, they have hardly any barriers here for which to fight through. That current sheet causes a drift that actually tries to keep them out. So these particles come in over the top. They have nothing to stop them. So you end up getting the maximum for a much longer period of time because this current sheet, which is wavy most of the time, but as it starts to flatten, cosmic rays can come in and exist over a much longer period of time during the cycle. But during the opposite polarity, where the field is now inward in the north and outward in the south, the drift patterns are actually the opposite. The cosmic rays come in along the heliospheric current sheet, and when that happens, the current sheet is very wavy, which it doesn't show it very well during sort of the end of the solar maximum as it's starting to go to solar minimum. It's very wavy, and the cosmic rays don't want to swim against that, so they get swept out. So it's only right when that current sheet is extremely flat that you get the full flux of cosmic rays. That's why it is a very narrow peak in time, and then it's flatter later. So this is the 22-year cosmic ray cycle. So I think I'll end there. And by the way, this is just a longer period that shows it that you get the peaked and flat top. But I kind of already discussed that. And I'll end on this slide. This is the Maunder minimum, which you've all perhaps heard of, is that during a period of time, which, side note, roughly corresponded to the life of Isaac Newton, by the way. Isaac Newton never knew a sunspot. Except for, I guess he was alive. So the last 10 years of his life, the sunspots started to come back. So he maybe didn't believe them, actually. That might be an interpretation. I don't know. But during that period of time, you might wonder, was there still a solar cycle, even though there were no sunspots? That's something of interest right now because the sun seems to be getting, at least we're having a weaker cycle. It turns out that, again, I don't want to put my full weight behind these studies because it's kind of an art form, and there's a controversy. But there have been studies that looked at tree rings and ice cores and plotted the cycle. So this is a period of time around the sunspot minimum based on tree rings. I think this is C14, and this is beryllium-10, that showed an 11-year cycle leading up to the time of the beginning of the Maunder minimum. And then after the Maunder minimum, you saw a 22-year periodicity in the cosmic rays. So there was still according to these studies, there was still a switching of the magnetic field polarity during this period, even though the sunspots went away. Okay? So the Maunder minimum may have happened, but the sun just didn't stop its cycle. Okay, I think I'll end right here, and we'll take, I guess, a break and come back, and I'll give the second lecture. Unless, I'm sorry, I should actually ask for questions if there are any right now. Yes? From the what now? From the which? Yes. Yeah, that's a very good question. That's part of the art form, I think. I think that you certainly could have, to produce gamma rays, they're pretty rare on the sun, but a really big event could do something like that. So they might show up as a spike. But any regular pattern would probably be galactic cosmic rays due to the cycle that I've talked about. Solar cosmic rays, yes, there's more of them during solar maximum. But it's really, there's the ones that what are referred to as ground level events. These are cosmic rays that are produced by the sun that actually can be observed by Earth-based detectors, are actually very infrequent. We don't see too many of those. So they would show up in records of carbon-14 and beryllium as a spike that's just kind of random that sits there. And even that is kind of a little bit debatable. The biggest event of them all, the Carrington event, was reported in one ice core. Okay? This is Dreshoff and Zeller. Wrote a paper showing this big, huge spike in beryllium-10, roughly corresponding with the Carrington event, and attributed that to a solar energetic particle event. But other ice cores on the Earth did not show that. Okay? Yeah. I don't know that they have the resolution in the carbon-14 to be able to do that, because this event doesn't last very long, and the tree rings are basically an annual thing as opposed to trying to see daily or weekly variations. I don't think they have the resolution for that, but it's certainly a valid question. So, but solar events show up typically as random spikes, but not very frequent because ground level events are very rare. We can count the number of ground level events we had during the last solar cycle, like 5 or something like that. Very, very few. Huh? Okay, 16. I'm sorry, I've been corrected. See, I'm a theorist. I just say, order of magnitude. Yeah. No, ask as many as you'd like. The neutrons? Okay, I'm not a nuclear physicist, so I don't know about there. It must be one of the byproducts of the nuclear interaction of these high energy striking. The particular composition of our atmosphere as well comes into play. The nitrogen and oxygen, the components of that. I have to admit, I've heard talks on that, and I don't have the background, unfortunately, for a lot of that. So, are there any other questions? You guys are all anxious to get coffee? And you can feel free to answer questions at the beginning of my next lecture. I don't have to give my next lecture. I can just answer questions, too. That's fine. That's fine. 25 till, okay.